So a brief intro. So Prathu works as a principal solution architect in NVIDIA. His background is in physics, and he has been associated with, he has worked at the Supercomputer Education Research Center of Indian Institute of Science, SERC as it is called. He was in charge of management, deployment, and user education of these high performance computing devices, and like which is used to run lots of scientific computations in physics, chemistry, atmospheric sciences, and so on. Like after like IISc, he worked as a lead software engineer with California Digital, and then with Z Research, and several other companies. He has also worked with Wipro for Infotech for a while, and since 2019 he joined as in NVIDIA, where he has worked like as an SSA and then as a PSA. So he mostly takes care of the big data, AI, ML, and HPC solutions. So he is going to tell us about the role of high performance computing in the like in scientific computing, including weather and weather and climate. So with that, I invite Prathu to start his presentation. Yeah.
Okay, so welcome to this session. I'll be mostly trying to answer your queries, how HPC and why there is so much hype about GPUs in AI and all. What is different in the computing in the GPUs? How do GPU augment sort of computing, and what ways you can program the GPUs? Okay, initially we'll start with that, and maybe if time permits, we'll talk about Modulus, which you might have heard about it. Modulus is a platform in which you do scientific computing or the physics integrated neural network programming. Okay. I'll talk about that, and later on I'll talk about our portfolio there with Earth 2 and ForecastNet. Okay. So it's a tall order. It just like weather code, it transgresses multi scales actually. So we start with very basic, and we call this. This is a part of actually a boot camp, which we hold to teach people about GPU programming. So it is important for you also to hear. I know that you get most of the tools ready-made and you are not very concerned about that, how the computation is happening in GPUs and CPUs and all that. All the libraries are already made and all that, but still someplace you might find that performance really matters. So there you have to know what goes inside it. Okay. So we call this N ways of GPU programming because earlier people used to think that only there is only way to just use GPUs, that is the CUDA way. Okay. Now CUDA is a platform which is written to, I'll explain it in deeper way later on, to basically utilize the hardware or utilize accelerator based technology which is there in the computer. Okay. So how do you do that? So there are different high performance computing things which came up. So sequential programming, you already know this, that there is a CPU, there is a memory, there is direct access to memory. All the programs which are to be run in CPU has to be there in memory. All the data as well as the code should be there in the memory, and it should be run out of CPU, and it's done sequentially so that everything is accessible. Okay. Now then came multi-threaded or the shared memory programming model, in which there are multiple cores or multi-CPU. The normal laptop you have is a multi-core system. all the cores access the same bank of memory. Okay. So different memory things people can access, different cores can access, and some way you can bring in the parallelism here. Okay. Then the problem here is, what if there is a memory location in which multiple cores or multiple CPU want to access that? What happens then? If same memory location multiple CPU want to access, then they have to be queued somehow. So when it is anything is queued, that becomes serial. That means it is going to suffer, performance is going to suffer. So the solution people came up with, that why don't I make one copy of memory for this CPU, one copy for this CPU. So you have multiple copies for different CPUs. That is distributed memory. So you are sharing instead of. But then another problem comes, that this processor will operate on this memory and it will modify it. This processor will operate on this memory and it will also modify it. How do they communicate this modified results? How this processor should know about this and this processor should know about this, right? So they come up with some protocols that after some time steps, I am going to communicate the results of this to this. So this is called distributed memory programming, and there are message passing or MPI protocols which are written for that. Okay. Now, where does the GPU fit in? So let us try to see. Okay, so there are the problem with serial programming or even the multi-core programming is that performance taper off. The performance does not keep on increasing, and it depends upon, it's very simple to program. Actually, the same code will work on year to the different processors. Higher speed processor, your code is going to run faster, right? That is the thing which happens year on year. You just need to buy a latest generation of processor and the code will run faster. That's it.
I just have a very question.
Yes.
Say,
Mhm. Yeah.
I mean, what technology, why it increases? I mean, what that you say new technology or costly? I mean, what is how are you making improve? Because you cannot make size bigger, I can understand.
Yeah.
Inside the chip, what is making nowadays the chip faster? How is that theory going on?
So I'm not saying it is becoming costlier, but it becomes actually not costlier, but actually it becomes slightly cheaper. So the thing is, how it becomes faster is they keep on reducing the device size. Okay. So earlier they were doing 7 nanometer or 12 nanometers or 15 nanometers, then they reduced it to 12 nanometers and then 7 nanometers. As the size of the device increases, you can increase the clock speed of the device and you can pack more of those devices in smaller area. So that's how. So when you go to 4 nanometers, obviously 7 nanometers is almost half, right? So you can pack number of devices, double the number of devices, right? That's how you make it. And as you make it smaller, you can increase the clock speed. As the clock speed increases, your device speed increases, right? So basically essentially to increase the clock speed, you have to keep on making the devices smaller and smaller, but you cannot make it further smaller. You cannot go 4 nanometer, even less or something like that, okay? So higher clock speed means low, the devices, That's why it tapers off here. And that's why if you work on devices with lower clock speeds, basically, then there is still place for improvement quite a bit. That's why this is linear, while this is tabling off, right? So basically, if you want more and more performance, you have to depend upon something else rather than just simple clock speed or sequential programming. What you have to do is essentially you have to think of ways to run the tasks in parallel. Okay, this slide I will take it little later, because this talks about multiple scales, okay? So now what is the importance of the engines? Okay, there are some devices which can run the tasks in parallel very well. Okay, so now there is a concept of there is a computer you have in which CPU systems is there, and you have put another system, another thing, chip or something else, which is supposed to run some part of the program much faster. So basically, you have this code which is running on a computer, and you have added a device which will do some portion of the program very fast. Okay, very fast means in very massively parallel way, high throughput computing. Okay, and this part of the code is still running on CPU. So model is that you have a computer on which one program runs, certain portion of that program will go on to the added device which is there, okay? Example I can give you is like this, okay? When you want to send a parcel, say from here to Mysore, if you have one parcel which is about 1 cubic foot or something like that, then how do you send it fastest? You will perhaps put it on a bike and send it through some bike rider. Just take the parcel to the Mysore, okay? If you have 5 such parcels, then you will hire a car, right? If you have 1,000 such parcels, what will you do? You have a truck, hire a truck and then send it across, right? If you have 1 million such parcels, then what will you do? Hire a goods train, obviously, right? So, but goods train is like, it is a massively parallel thing, right? At one shot, 1 million parcel will reach Mysore, right? At one shot. But there are things which you have to shift the parcels to station, load it onto the train, we sent it to Mysore, then unload it, then again take it to the godown, right? All those things have to be done. So GPU is like a goods train, actually. When you have lots and lots of computation to be done, then use GPU. But for all the things have to be shifted to parcels to be different sides to be shifted, you use CPU basically. So all the serial tasks are done better on CPU, and all the parallel tasks can be done better on GPU. Lot of computation can be done together onto can be done on GPU. So the code runs basically on main computer, on CPU. There is a portion of code which has to be offloaded to GPU, and rest of the code will still run on CPU. So this is where you are reading a file, inputting some data, then you are doing this massively compute parallel things onto the GPU, and then later on post-processing the data, writing the two files, all these things again are to be done on CPU. So for this to occur, you have to have ways to tell in the code that this portion will actually go onto a device or the GPU. This is where CUDA programming comes in. It gives ways to tell in the code to compiler that this code will be compiled for GPU, and at runtime, this has to be executed onto GPU. This is what CUDA programming does actually. Okay. So does everything work well on CPU and GPU both? It is not. So for some things, CPU is better, something is GPU is better. Let us see what. Okay. CPUs are optimized for serial tasks and GPU is optimized for parallel tasks, but I can also add a word, massively parallel tasks. It's like a goods train. When you have million parcels to send, then you use GPU. Even 1,000 parcels might not be so efficient to send on. Means that much computation also might not be so efficient, okay?
Is there a scientific definition of massively parallel, or what we will call normal parallel, or is massive? I mean, limit on some scale.
Yeah, so I'll give you the limits, okay? So the CPU has how many cores? That is the scale, that will define the scale, okay? CPU has maybe up to 20 cores, 32 cores, and GPU has around more than 10,000 cores, 12,000 cores. That is the ratio, how much parallelism you can have. So there are some other factors also which come into the thing, okay? So silicon budget wise, CPU has less ALUs. Obviously, it has less number of cores. It has more control and it has hierarchy of caches, because in CPUs, what happens if you miss there is a caches miss or the memory is not there, the data is not there, then you have to access to the memory. At that time, these misses are costly. So a system of caches is built in to minimize that cost, okay? In GPUs, on the other hand, ALUs, because there are so many cores, right? More than 10,000 cores. So ALU is so much more. Control is less because so many things to control, right? And the caches is relatively less. Yes. Huh? Yeah. Arithmetic logic unit. There is a control processor which basically tells that when the program comes, it sends to different units. There is memory access unit, there is LU, all those things. It will keep on sending the program. So that is the control. And caches, you know, when anything to be processed on a system, it has to be there in the registers. Two numbers have to be there, added, they come into registers, they are added, and the results are again put in the register, right? So these two, that data has to be there in those registers. If it doesn't find that data in the register, it will send a memory fetch notice. It will go and fetch from the memory. Whenever this fetch from the memory occurs, then it takes lot of computational cycles. See, addition can happen in one cycle, but this fetch from the memory can take hundreds of cycles. So that much costly it is. So when this is costly, then what they do is that they, instead of getting one data, they will close to the registers, they'll keep some memory space which is very fast, from which you can quickly get the data. So from there, bring a bunch of data and keep it in the cache, okay? What is the guess? That this data is required, the next data also might be quickly required, okay? So that is brought in here, and quickly it can be accessed. So in CPUs, there is a system of caches, L1, L2, L3 caches are there. Basically, bring this much data, put it in L3 cache. From there, it takes so much data. I can give you an analogy. Like, there is, if you are painting a house, okay? So you have asked the teams to paint the house, say, on first floor. He has a paint box and a roller, okay? He dips in the roller and paints the wall, okay? Once that box is over, then every time if he has to go to the ground floor and from drum he has to fill the that box and bring it, it is going to cause him every time. Because this will, in 5 strokes, it will become empty, right? So what they do, instead of that, they make a smaller box, take it and keep it in the first floor. That is the same analogy as cache, right? So it has a system of caches which will try to minimize the latency of what memory or data misses, okay? It is about GPU. So ALU, the arithmetic logic units, obviously so many cores are there. So it is going to be more. And so many cores are there. So control is also cache is less. Control is less because there are so many LUs, no? So many things you crowd control. Huh?
The control less in GPU, is it because there has to be more communication between the
Yeah, you can think of that way also, okay? So some of the things which come to mind: very large main memory, very fast clock speeds for CPUs. Latency is optimized by large caches, and small number of threads which can run very quickly. So serial programming can run very fast on this, okay? And if some lower level of parallelism, that can also run faster. But it has relatively low memory bandwidth. GPU memories are generally put with very high bandwidth, okay? Cache misses are going to be costly compared to the clock cycle, and low performance per watt, because as the clock speed increases, the power consumption of the is also increases, okay? On the other hand, The GPUs has high bandwidth main memory, lot of compute is available. That's why when we say massively parallel, it will run very efficiently on GPU. That is, the ratio is similar to that, number of cores, right? And it is, one important thing is it's latency tolerant. In CPU, we try to minimize the latency by developing a system of caches. Here it is made latency tolerant because you have so many lightweight threads to play around with. You can actually keep on scheduling the threads one after another. And this way you can hide the latency, okay? The memory misses are still going to be costly, but you can still hide them, okay? And high throughput and high performance per watt. This is what drives these days the data centers, okay? You want data centers to have high performance per watt because power consumption can be a very significant factor. Per thread performance is going to be low in the CPU because it's running at lower clock speeds, basically. So how does it hide the latency? You see that T1 has asked for some data to come. One thread is launched. So lot of lightweight threads are launched together in GPUs. And if T1 is waiting for data, you launch thread 2, thread 3, thread 4. By the time you see that thread 1 is already beginning to get his data back. Even more, actually, you can launch many more threads. Okay. Same analogy which we have given earlier. Now we'll go back to the previous slides. So you have programming at all hierarchical levels, actually. In GPUs, they're organized in some way. It is called ESMs. Okay. It's a little bit more technical term, ESMs. It has multi-cores inside each SM. Okay, multiple cores. Why they are organized in this SM frameworks? Because they share something called shared memory. Okay, the devices around that shared memory. So basically, there is a thread block programming model which happens, which is just logically you put blocks onto SMs so that they can share the memory. Okay. So multi-SM makes one GPU. Multi-GPUs make a multi-GPU system or multi-node like DGX, and multi-system rack. So you have hierarchy of scales. At all scales, you need to think about programming into this kind of things. Okay. Take advantage at all scales, basically. Here you take advantage of shared memory. Here you take advantage of single GPU. Here you take advantage of single system with faster connectivity. And yeah, so there are various ways you can think of programming. Okay, node scope, there are libraries. CUDA toolkit is there, which can be used to, which has lot of libraries and all. So I'll talk about libraries in few slides. Okay. But if you want to do basic programming, then there is CUDA C++, and for domain people, OpenACC is very much there, which can be learned in half a day or so, okay? So NVIDIA comes with different hardware technologies like GPU, switch, and switches which are giving interconnects, then servers and cloud, which you can access the GPUs and compute technologies. On top of this hardware, there are acceleration libraries and platforms like CUDA built on that, and some basic libraries like BLAS, CuBLAS, CUFFT, and things like that are built on top of this. In turn, using this, there are platforms and toolkits built on that, okay? Like TensorFlow, in turn it uses this library, which in turn uses efficiently this hardware, okay? That's why you are not really bothered about how to divide the task into GPU and all that, because this is being done at this level, okay? TensorRT is the inference platform. HPC SDK, if some people are working in NWPs, then they will be concerned about this, HPC SDKs. And some people, if they are working on visualization, they'll also be working on this, these platform, index and optics, okay? Then application frameworks are there, okay? And there are platforms like Modulus built on top of that, okay? So when we talk about why do you think we have so many parallel processors available? Can you guess? What kind of tasks are parallel? Huh? Huh. Matrices can be done parallelly. Okay. So if I have a particle which I want to evolve, say, in its trajectory, one after another second, is it a parallel task? No, it is not parallel at all, right? And but if we have 100 particles which we want to evolve, then is it a parallel task? Because each particle can be evolved separately. That's basically the concept what the molecular dynamic people use it actually. Because they are trying to evolve thousands of molecules and they are tracing their trajectories, right? And they interact with some kind of inter-particle forces, which can be electrostatic, electromagnetic, their long-range interactions and things like that, okay? So that is parallel task. Now, why AI is being hyped about in GPU? Is it massively parallel or? Huh? It is not kind, it is parallel. Because why do you think it is parallel?
The numbers of its own layer. So you can evolve layers with time.
That might not be true, but basically what does training process is supposed to be very parallel. So training process involves what? Taking examples, right? Examples one after another, right? Each example can be an independent task, isn't it? It is a parallel task basically. You can place 10 examples together without affecting each other. You can take 100, you can take 1,000,000 examples together. It's embarrassingly parallel. It's just parallel, right? Besides that, inside you are dealing with matrices, which is another. He said that it's a parallel task. So its hierarchy of parallelism is available in AI, right? You are training through examples, then again through you are dealing with matrices. All those things are parallel in nature.
Sequence to sequence model.
Huh.
Earlier generation, before the transformer,
Huh.
it could not be processed parallelly, or it could be processed like RNN.
Huh.
So where we take one text at a time.
Hmm.
So those are parallel tasks, or those are examples of serial tasks?
Those are serial tasks because it is evolution, just like particles trajectory, that has a time series. Time series which is sequential task, right? Time series, it depends upon previous layer or previous word or previous this thing. So it is a sequential task evolving it. But when you came to the transformer based architectures, then it became parallel because you are then taking encodings and vectors. Okay, I know you might not be so much interested in programming, but still, if somebody is interested in programming, then there is HPC SDK, which comes with all the things. NVCC, which is the CUDA program compiler, okay? And then these libraries are there, CuBLAS. So if you are using some say BLAS or some such libraries, then this can be replaced with CuBLAS and you already make it available on GPU. The code will be ported to GPU just by using, instead of BLAS, CuBLAS. Okay. Some things are written specifically for GPUs like CuTensor, then CuSparse, CuSolver. You are using LAPAC, then you can use this CuSolver. If you are using FFT, then you can use CuFFT. And so that is, now math libraries, when we say that math libraries are best way to do the GPU enablement, this is because the libraries are developed by, first of all, engineers, so they are written very efficiently, okay? Then it is tested thousands and millions of times. The libraries, users world over use that. It is tested, any bugs are there, they are reported and they are worked upon. So the results are guaranteed, the results are verified, and also the performance is verified. Performance is also guaranteed here, okay? So the libraries are best method to, in case somebody wants to work on enablement of GPU, enablement of code, then library is the best way. In case the functionality is not available in libraries, then you think of CUDA or OpenACC. Now there are tools. So even if you are not working on directly coding, still there are tools called profilers. Profilers basically give you an idea. When you run the program through profiler, it gives you an idea where the time was spent in the program. whether it was spent in communication or it was from, we saw that from CPU to GPU, you have to transfer the data, right? So in that communication or between node communication or where exactly it spent the time, that is the job of profilers, which portion of the program it spent time. So even if you are directly working on library codes or the platforms, still it is important to know where your code is still running very slow. Even if you have used the best possible method, then it is running very slow, then you run it through profiler and find out where it has spent time and which portion. And perhaps you can adjust that. Perhaps you have given the batch size too small or batch size too big or things like that, that can help you to program that better, okay? CUDA GDB is a tool which basically gives, it is more of interest to programmers. It gives where the errors happened and things like that. And you can trace back all the errors, okay? And you must be familiar with containers. Container is inbuilt. You can have a container in which you can have all the dependencies installed and have a container runtime, which will run with all the dependencies. So you don't have to install everything afresh. Okay. I'll skip some of these slides. Yeah, libraries, I talked about them. Okay, I'll change the presentation and talk now more about modulus.
Elaborate more on this accelerated platform, how we actually accelerated. It's not at the accelerated platform does not come into the picture there, correct? How do you actually use? There are so many features in accelerated platform. So at what level do you actually make use of this, harness the benefits of accelerated platform?
I'll just go back to that slide.
One may have laptop in the GPU part.
This. Okay, so basically this is accelerated platform means NVIDIA provides all these things with complete stack. Okay. So you have hardware technologies like GPU. Okay. So GPU as such directly, the coders might directly work on GPU or something, but it doesn't help, right? GPU is there. You are, you cannot use it. So there have to be tools.
NVIDIA provides all these. It's going to be the software form that's going to all these supports.
Yeah. Hardware, then this servers anyway you can check, but basically it comes from these libraries and the platform, the CUDA.
Not of overhead level. I may not use all the utilities at one time. I may use it one. But all the time everything is available means it's a load on the system to keep track of everything. How does it accelerate?
No. That is not the thing. Whatever you require, you can keep only those things. You need not. It is provided everything.
You said NVIDIA provides all this. So accelerated platform is a format like this. Okay, there are a lot of features in that. So you only access those features when you want, and the rest of the features, what happens?
So these all things are provided by NVIDIA, but whenever you require, say for example, smart city, if you are working on smart city, then you just use this smart city, and there are ways like NGC. Have you heard of NVIDIA GPU cloud? NGC containers are there. You just take Metropolis container
You
and
mean to say these are there, and whatever I want to use from the container, only use that one.
yes,
So only that part will be installed in one.
yes,
The general facilities available in the pack there.
yes,
If you want to just use it.
yes, exactly.
So it's not that every time all the packets are.
No, 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 no.
It's not, it's an independent individual.
Yes, individual things. If you want Metropolis, a smart city project you are working, you just use Metropolis. If you are working in HPC, then you just take HPC SDK. If you are working in healthcare, then just take Clara. That's it.
I'm using an application where I have smart city and I also have HPC and I also have healthcare, but all of them I don't need at one time. Suppose I call the container to put all these things. They will become overload. I want to use only smart city. I want to now do away with it. Then again call the other thing.
Unload that container and use the Clara container.
It will be removed from this thing. There is also a container which is going to fill in all the things, and they also kill all the things back. That's also possible. Dynamically, call the things and use it and then throw them back, like managing dynamic memory.
Those kind of things are also possible with what is called blueprints. Okay, one after another containers. You are making a workflow. So one container is used, then it's removed. Actually, there are some things called container maker. Okay, when we are making a container, no, then if we are say using an HPC application for any say WRF, okay, then I'm going to install, initially I'll require all the compilers, okay, because I'm going to compile the code. Then I install those compilers in the container, compile the code. After the compilation is over, I don't need compilers, right? So I'll remove those compilers. So my container becomes still lightweight. Only executable binaries will be there.
So it can be very dynamic on the go. It can use it and then throw it back so that
yeah. So container itself, you can develop your own container also by using this. Okay, and your container can be
make your own container where you want to use it, generate it and throw it. So
yes.
Container building and container, you should make a container of your choice.
Yes, yes. You can make a container of your choice also, so and you can distribute it.
Whatever it is in terms of kill whenever it is not.
Yes, and it will be so lightweight you can distribute it.
Very, very useful things. So does NVIDIA provide any facility that container generation can become very simple, because somebody need to know how to deal with the container.
Yes, there is.
User-friendly way of I just give a list of instructions, the container should
yes, yes.
Generate and kill it.
Yes, yes.
Support.
That support is there. That is called HPCCM, HPC Container Maker.
Okay. I can just specify it easily and then it will take care of it.
Yes, you can pretty easily take care of. You can say that install compiler. After that, remove compile, remove compiler.
Simple as that. Okay.
Yes.